Really quick test review. I'm going to try to go through it as quickly as we can. We've already gone over all of this, so nothing new here. When we first start talking about electricity, we need to make sure we're talking about electrons. So as we talked about, electrons are the part of the atom that have a negative charge. They can hop off of one atom and go to another, and their movement or their flow is what we have as far as electricity is. So when electrons are flowing, that's going to give us our electricity. Electrons, when we talk about them as being negative, that's really just describing a behavior. Some of these subatomic particles attract one another, some of them push each other away, some of them don't have any kind of interaction. When we see electrons, we describe them as having a negative charge. In reality, really what that means is that when we get like charges, if we have two negatives, they tend to push each other apart. The same thing would happen with two positive charges, which is not all that necessary for us with electricity. But if we get positives and negatives, then we do get a sense of attraction. We can draw what's known as an electric field, and these lines around the electric field kind of indicate the strength of the attraction with the electricity, and we see as we get closer to them, they're closer together, so there's a stronger attraction. And what we see is, in this case, arrows are pointing towards the negative charge, and they point away from the positive charge. So when we have these field lines, we just want to kind of keep in mind that the arrows are going to be headed towards the negative charge. Since it's an electric field, they're going to be moving towards that negative area there. We can get electricity to flow for us if we get a certain setup. So if we have some wire, we have a voltage source, and we have something to put on the wire, we can get a circuit. So basically a circuit is a complete pathway that our electricity can flow through. Well, we've got two different types. We have a series circuit and we have a parallel circuit. When we have a series circuit, notice the similarities for each of these. We both have a voltage source like a battery. In this case, we have a switch, which is not necessary to have in a circuit, but these are drawn as such. And we also have some wire. Both of these are the same in all of those respects. What's different is the order in which the resistors are put into place. In this case, these are bulbs. In a series circuit, there's only one pathway for the electricity to flow. In other words, the electricity cannot get from one side of the battery to the other side of the battery through any way other than going through both of these bulbs, assuming that the switch is closed in this case. Contrast that to the parallel. There's multiple pathways. So electricity can flow through this path, and electricity can also flow through this path. Because of this, there's some very small differences between how these operate, but they're pretty substantial in terms of kind of their purpose that we would use with them. All right, so the big thing is, again, parallel is going to have multiple branches. That doesn't just mean that there's parallel lines on it. That's not the whole thing. But if it's parallel, that means that there's multiple pathways that the electricity can flow through. The thing is down here on the series is that each light is dependent on the other. In other words, this light is not going to be able to work unless this light is working. If this light is working, then effectively this, like a switch is here, the electricity can't get through it. If the electricity can't get through it here, the whole thing stops working. The electricity cannot flow. So effectively, for electricity to flow, we have to have one complete pathway of uninterrupted circuitry that's going to allow it to work. Over here with the parallel one, if this top bulb, for example, burned out, there is still a pathway that allows the electricity to travel in a complete loop. And so this light bulb would tend to stay on. So we would say that these light bulbs tend to be independent of one another. So one of the big advantages over here is that if one bulb goes out, the other bulbs should stay on. Whereas over here, if one bulb goes out, all will go out. In our home, things are wired in parallel, which is nice. That way we don't have to have everything on at the same time. So in a series circuit, everything has to be on or nothing is on. It's either all or nothing. Whereas in a parallel, we have the ability to turn certain things on and to turn certain things off if we need to. When we're describing a circuit, we can quantify or put numbers to the various parts of it. So as we build the circuit and as we have things going through that circuit, we oftentimes want to say how much of a current do we have, or how much of a push do we have, or how much resistance do we tend to have. We can make this relationship in Ohm's law. Often in class we've been writing it as V equals I times R. Probably the more useful way to think about it is to rearrange our formula so that it looks like this. And the idea that it's the amount of current that's going through the circuit is proportional to the voltage. In other words, if the voltage goes up, then the current is going to go up. And it's inversely proportional to the resistance. In other words, if we increase the resistance, the current's going to go down. You can oftentimes think about this being really similar to how water might flow, where voltage would be almost like the water pressure. If you had a hose and we're turning it on the spigot, so we could change the voltage based upon how much we turned the knob on the water. Obviously, the more we did that, the more current, or in this case would just simply be the amount of water coming through the hose, would increase. So if we increase the pressure, we're going to probably increase the amount of water. Conversely, the opposite of this, resistance, would be like squeezing the hose, or having a skinnier hose, or having a longer hose. All of those things would increase the resistance. It will make it harder for that water to flow. So anything we can do to increase the resistance is going to have a negative effect on the amount of current. Oftentimes when we're building a circuit, we don't really have any control over the voltage. The voltage is the voltage. If we have a battery, maybe it's a 9-volt battery. We don't really have a slider on that we can change with it. The amount of current that's going to come out of this battery depends upon what is it that we're hooking up to it. So how many bulbs, what refrigerator, television, all those types of things. The number of things that we're putting on this wire set is going to determine how much electricity is going to be able to flow through it. So if we put more things on, there may be parts of it that have more or less electricity that's going to be on there. So again, typically as we increase the resistance overall, we're going to have less current. That's what this formula tells us, and then there's going to be examples where we may have to work some things out given some of the information that's on there. These are the three parts of our circuit. We've got our current, we've got our voltage, and our resistance. Again, current is the amount of electrons that are moving. We can increase it, we can decrease it. Generally, if we increase it, there's more going to be available to do more work, which we could kind of translate into the brightness of a bulb. So in general, if we get more current going through a bulb, we're going to get a brighter bulb. And the idea down here at the bottom is that if we increase the current, we're typically going to get a brighter light. All right. So how do we get more current? Typically the way we're able to get more current is, one, we may need to have more voltage. Voltage can be described as the electrical potential. The electrical potential, it's kind of like the push that we might have on something. It's a potential energy issue. And sometimes it can be described as just a potential difference from one side of the battery to the other, or from one side of a electrical outlet to the other. So the greater the voltage, the more potential energy that's going to be there for it. There's some definitions that relates into joules and those types of things. So again, if we want more voltage, we need to add more batteries, or we need a stronger battery. This would be a dry cell battery, which would have chemicals in it. If we had a couple of AA batteries put together, which are 1.5 volts each, we would just add them up to get the 3 volts. Again, it says that more voltage is like a stronger pump. And so if we increase the voltage, that's going to correspond to this column. We're going to get an increase in the current. Current is measured in amps or amperes. We use the letter I to symbolize it. Voltage is measured in volts, which we use a V. Nice and easy. Now the resistance is what slows down the current. This is the things that we would use if we were having a water hose to squeeze it to keep it from moving. If we add devices in a circuit, that's generally going to increase the resistance of that circuit, particularly if it's a series circuit. So in this case, if we had 6 volts and we resisted it with 3 ohms, which is our unit for resistance, we would end up having 6 divided by 3, and we would get 2 amps of current. If we had 2 bulbs, we would add these together. We would have 3 plus 3 since they're in series, and we would still have 6 volts, but now we have 6 ohms. 6 divided by 6, notice that it's going to drop our current. So what we would also find is that these light bulbs in the same situation would end up getting a little bit dimmer because they're having to share the current, and it ends up having a little bit less current to be able to go through it. In addition to adding things to the circuit to increase resistance, the wire itself might have a little bit of resistance. So you might think about it as if we had a skinny wire versus a fat wire, that this one's going to have more resistance. It's going to be harder for the water to go through a small hose than a large hose. So similarly, it'd be harder for the electricity to go through a thin wire than it would be a thicker one. And additionally, the length. If we have a very long wire system versus a very short one, this one's going to have more resistance because it has a longer path to travel, and this one would have less resistance because it has a shorter length to travel. We also then moved on to magnets. Magnets are related to electricity because magnets do what they do because of the electrons that are in them. So a magnet is something that can attract metal or another magnet. It can also repel another magnet. We talked about that they have different poles to them. Again, what happens with the reason why a magnet's a magnet is the electrons that are in them have a spin to them. And if the spinning of the electrons in those atoms all tend to line up, then that's going to make the material act as a magnet. So we do have, in ways, a lot of the things about the magnets are similar to electricity. Now, magnets don't have an electrical force, but they do have a magnetic force, and that magnetic force can be kind of similar to the electrical force in terms of the way we think about them. Magnets can be permanent, like a bar magnet or horseshoe magnet. They can also be temporary, and those would be like an electromagnet, something that we would have to hook up electricity to be able to use in order to attract things. Just like with an electrical field, magnets have a magnetic field, and we would represent them as well with these negative charges. So just as before, when we had electrons, lines, electric fields came to the electron, the negative charge, and then they went away from the positive. In a way, a bar magnet would be kind of the same thing. So we have a south side, and you can see that the lines are coming towards it, and there's a north side where the lines are coming away. So in a way, it's kind of like the south acts as the negative does compared to the positive when we do charges. Now again, magnets and electrical, the forces are different, but they have similar behaviors to one another in that north and south will attract one another, south and south would repel, north and north would repel. Likewise, plus and minus attract, but plus and plus or minus and minus would repel one another. So as mentioned previously, what causes the magnets has to do with the spinning electrons, and permanent magnets have the electrons always lined up in the same direction. We call that a domain, or and the idea with a domain is if we drew it out, it would be that the magnetic force of each little tiny piece would all be pointing in the same direction, and from that it would end up being magnified. Again, a temporary magnet, in order to get them all lined up, we need to usually hook it up to an electrical source to be able for it to work, and I'll go back to this up here in just a second. We can look at the electromagnet. Again, we have a magnetic field that surrounds the magnet. The lines are always going to head to the south and away from the north. We see that as we get farther away, the field gets weaker. The strength is going to be greatest at the poles on this, and that we can also cause a compass to interact with this simply because the Earth has so much iron in it that the Earth acts as basically a giant magnet, and so we can use something like a compass to be able to point towards what's technically is the magnetic North Pole. because of the iron that we have inside of the Earth. Now, an electromagnet, in order for us to use it, as we saw before, we need three components to it. We need usually a core, which is going to have, usually it's going to be an iron-filled piece of metal, like an iron nail. We have wire that wraps around it, and eventually these would need to tie into a battery source for us to get the electricity to go through it. So we can strengthen the electromagnet in several ways. Now, we want to increase the electricity. So if we want to increase the current, then we would need to increase the voltage. So if we get a stronger battery, that would work. If we wrap more coils of wire around it, that would cause there to be more electricity there as well, which that would increase the strength. And if we get more and more iron to be able to put into the core, that should strengthen the electromagnet as well. We also spent a little bit of time with our PhET simulation discussing how there's a relationship between magnets and electricity, that if we move magnets, we can move in a magnetic field. If we move current, we can generate a magnetic field. If we alternate current back and forth, we can flip a magnetic field back and forth, back and forth. And if we take that electric field and bring it near another set of wires, we can induce an electrical current with it. So if we have an alternating current flipping back and forth, back and forth, back and forth, the surrounding magnetic field will also flip back and forth. If we bring into proximity another set of wires, that flipping of the magnetic field will cause the electrons in that wire to be able to move, which can also be able to generate electricity. So we have another number of things like transformers, motors, and generators that can use this relationship between electricity and magnetism for useful purposes for us. All right, and the last thing I want to go over is just a comparison and contrast of a couple of different types of circuits that we might have. Hopefully by looking at these, you would be able to note what's the difference, like if we just classified them. The one on the left over here, this is going to be our series circuit. There's only one pathway that the electricity can flow through, whereas this one over here on this side would be a parallel circuit because the electricity would be able to flow in multiple pathways. A couple of things we see is that every bulb in this one is the same brightness. If we broke the wire, they would all go out. If we added another bulb, then the current has to get divided up a little bit more, and then what we would see is these would all dim just a little bit. So as we add bulbs, the resistance goes up, and the current, remember, which is the letter I, would end up going down. The parallel circuits are a little bit more complicated because there can be a different amount of current in every single area. So the amount of current here is not the same amount of current that is here, and it's not the same amount of current that's here. Now, these B and B would have the same amount of current because they're on one pathway, and they're the only bulb on that pathway. So effectively what we've got is we have three pathways in this one. This is probably more complicated than anything we'd see on the test. But we have three pathways that the electricity can go through. So if we were to assign a number to these, the amount of current that's going through here, for example, this one might be 10 amps of current. Well, this one would also be 10. And the reason why is it has its own path, and there's only one bulb that's on it. Path 3, we would expect still to have 10 amps of current going through it, but this is effectively like a series. And so each of these would be 5 amps. Because the bulbs would get a little bit less, and so there would be 5 amps of current going through the top part. This bulb down here in the bottom, A, would be the brightest of all of them because it would be all of the current basically added together that's going through this entire amount. And so as I mentioned before, that's one of the dangers sometimes that we might have is actually the amount of current here depends upon all of these branches. And with a parallel circuit, oftentimes the more branches we add, the higher the possibility is for us to get more and more current right here, which is why we discussed the idea of having circuit breakers in case we get too many things running at the same time on a parallel circuit, because every time we turn something on, it's going to make the current go up through this portion down here. The reason why is there's nowhere else for the current to go. It only all the current has to go through this bottom part. There's no alternate pathways for it to go through down this bottom part, whereas through the rest of the circuit, the current can get divided up into various types of places. So if we went back and looked at all this, if we added bulbs, if we added things in various places, so for example, if I added one more branch to this particular circuit, if we put another bulb up here, it should be the same. I remember I had these labeled as B. That should say this would be the same brightness as B and B. Again though, if we did this, then because this needs more current, this one now would end up getting brighter than before.